Hi, everyone. Today we're going to give a presentation entitled, I am the 100% asterisk, terms and conditions apply. What we're really going to talk about is reliable exploitation. What it means for a bug to be reliable. Sorry, my mic isn't working here. Can you hear me now? Okay, sorry about that. What we're really going to talk about today is reliable exploitation. What it means for an exploit to be reliable, and what are the properties of both the exploit and the underlying bug that make it reliable. We'll also present two exploits that we've written that we think are 100% asterisk reliable, and explain how they work and what the factors are that make them reliable. But before we begin, I should introduce myself. I'm Natalie Silvanovich, and I'm a security researcher with Google's Project Zero. And the second half of the presentation will be given by Chris Evans, who, in case you missed this morning's keynote, is Project Zero's fearless leader. And when we started talking about reliability, we realized that a reliable exploit can mean a lot of different things. Obviously, at the most fundamental level, it means that the exploit always works. Every time you run it, you load it in the browser. The code or whatever payload you have gets executed. But within that, there can be a lot of different subtleties. For example, does it really need to only work on one version or platform, or does it need to be multi-version and multi-platform? Also, does it need to work with advanced mitigations such as CFG? Also, does execution need to continue cleanly post-exploitation? Is it okay that you load the vulnerable thing and it executes code and then the target crashes? Or does it need to exit cleanly after execution has occurred? And also, does the exploit need to be reentrant? Does it need to run more than once against the same host? Or is it okay if you just run it once on a clean host and get code and that's it? Also, does it matter if the exploit takes a long time or uses a lot of memory? Do you have to worry about the user canceling? Or is it okay? Do you have some time to wait? Also, if it fails, what happens? There's really two things that can happen here. Either the target can crash, or execution can still continue. It will exit gracefully. And for the purpose of this presentation, we're going to call that an abort. And crashing is bad for a couple of different reasons. First, it's kind of a noisy signal. If someone opens up something and it crashes, maybe they'll think they're being attacked. Also, in some situations, if you abort, you exit gracefully, you get a chance to try again. Maybe if you attack something and then there's an exit, you can throw the attack at it again. But then maybe if it crashes, the process won't come back and you've lost your chance. And the more we talked about it, the more we realized that what reliability means really depends on the class of attacker. For example, for a profit-motivated attacker, say a botnet app operator, they really want to be able to throw an exploit out there and compromise as many systems as possible. And maybe they don't know a lot about the systems, and if someone opens up something and gets a crash and gets a bit suspicious, it doesn't really matter. But for the purposes of this research, we decided to think a bit more about targeted attackers. These are the types of attackers. They are trying to attack a very small number of targets they know a lot about, but every time they aim at them, they want to hit. And if they do miss, they want to not get caught. So with that in mind, we came up with this definition of reliability. An exploit is 100% reliable if it's guaranteed to succeed against a specific version and environment. And how would we ever know that? Well, for the purposes of this research, it's because we fully understand the exploit. Because we understand both the system we're exploiting and the exploit to the level that we can go through every step and say that it's deterministic, there's no entropy, and we know that it will succeed. But you'll notice this definition has an asterisk in it. And that's because neither of these exploits at this point are perfect. They'll still, on a small number of situations, come up to cases that we can detect, but we aren't able to get around. So in that small number of cases, we've decided it's okay if we go with 5 nines of reliability, and in a small number of cases, abort. But these exploits we think will never crash. So the next thing we wanted to do was to look for some bugs that we thought could be exploited reliably. And I came across this quote. Shakespeare generally had a limited amount to say on exploit reliability, but there's this. Some bugs are born reliable, some achieve reliability, and some have reliability thrust upon them. And we found that this was generally really true. There were some bugs that really lent themselves to reliability really well, and some of them we had to work a bit harder at. And the other part that is missing is that some bugs were born unreliable and will never be reliable, and there's nothing you can do to help them. So one such bug class we found was heap overflows that go over the chunk boundary. These can never be reliable for two reasons. The first one we thought of is when you're exploiting a heap overflow that spans chunks, usually you're relying on that next chunk being something specific. And that's not always guaranteed to happen. Heaps are big, complicated systems, so you can never really be sure that exactly what you want will be there. But then we got to thinking, well, what if you can read to check and make sure it's okay? But even then, you have this problem of what if you're the last chunk at the end of the page? Then if you try and read, you'll get a seg fault, and then you'll crash. So there's really no way, or at least none we could think of, that you can exploit this type of issue 100% reliably. The other class, which we think is maybe 100% reliable, but probably not, is use after freeze. And that's once again because they have this same problem where when you use after free, you're freeing something and then you're waiting for it to be reallocated and you're hoping that something specific is there. But what if it's not? So maybe you can find a special use after free where you could read and make sure everything's okay. But we think most use after frees can't be 100% reliably exploited. Now there are three classes we think can be exploited in this way. The first is the heap overflow within a heap chunk. Because in that case, you're really overflowing into other parts of the same object or whatever is allocated there. So in some situations, you could probably guarantee that those are the same thing, and then there's going to be no entropy in your exploit. Likewise, stack corruption. Usually with stack bugs, every time you hit the bug, the stack is laid out exactly the same way. There's things like stack cookies you'll have to get around, but generally, if a field is in a specific place, it's not going to be in a different place the next time you exploit the bug. So it's possible to probably do a 100% reliable stack bug. And the final one is type confusion. If two objects are type confused and the fields line up, usually that's deterministic. So it's possible in some situations to do a reliable exploit with type confusion. So we're going to go through two different bugs here. I'm going to start with a type confusion bug, and then Chris is going to present on a heap overflow bug. So the bug I exploited is CVE 2015-3077, which is a type confusion issue in Flash. I reported this one in February, and it was patched in May. And this, I think, is kind of an ideal bug for reliability. The sort of bug that Chris is exploiting is a little bit more generic, the heap overflow, but this one is kind of a special bug that's a bit unusual and lends itself to reliability really well. So this is the bug. And this code is really complicated. Unfortunately, on the margins of validity, ActionScript especially, the compiler stops working really well. It either compiles stuff so the code doesn't work the way it's supposed to, or it doesn't compile. So this is what I had to do. This is a simplified version. I promise that logically it's exactly the same code, it just won't compile. And basically what it does is there's this Flash class called a blur filter. So it creates a blur filter, and then it sets the object.filters setter to this filter. And the object is either a movie clip or a button, and it has this set function. And basically what it does is the object, you set the filter, and it copies the native object for the filter, and then it creates a pointer to it in the object, and then it just stores it. And then what I do here is I overwrite the blur filter constructor in ActionScript with the convolution filter constructor. And then I get the filters object. And you can imagine where this goes wrong. The getter, what it does is it takes this native object it stored and copies it into the new object. And then in ActionScript, every object has a native backing and then an object in ActionScript with a pointer. So it uses the constructor to create the ActionScript object, except it's now a different type because it's initialized using the convolution filter constructor now. So this allows you to create an inconsistent object in memory, basically. In ActionScript, it's a convolution filter, but in native objects, it's a blur filter. And this is quite bad. This is fundamentally what the issue will let you do. These are all the different filter classes, and there's other ones I didn't include. And basically, you can create any of these objects. You can set the members. You can get the members. Then you can cast it to the next type. And then you can get and set those same members. So there's some really interesting things here. You know, floats can be confused with pointers. Pointers can be confused with floats. They can all be confused with ints. So there's really a lot of opportunity here. So the first thing I wanted to do was to bypass ALSR. And I did this using this displacement map filter, and I confused it with the bevel filter. So that's what happened. And then I was able to fetch this pointer and fetch it using the color properties. And you can see there's an example of what the code to actually do this looks like. But unfortunately, this is just a pointer to the bitmap data, not to the vtable. So I had to do it one more time. I confused this pointer to the bitmap data with a pointer to a float matrix. And then I can fetch the two pieces at the beginning. That's the vtable pointer. And then I have a pointer to the vtable. But then there's a problem, floats. This is the floating point specification, this table. At least I think it is. I've never completely ruled out the possibility that the IEEE is trolling me because it's just so complicated. And it has a number of problems, especially if you're trying to cast pointers to floats. For example, there's the code below, which is a float that in memory is 7FFFFF. And if you decrement it and then you access it again, it's still 7FFFF. And that's because it's a nan in floating point. And those values can be represented as anything, including 7FFFF. And they're often corrected in C to be a different value. So there's a few things I thought I could do here. I started off by writing a float converter. Been there, done that, got the off by ones. And then I discovered that this actually wasn't possible because in most script interpreters, including ActionScript, there's no casting a float to an int. So if something's a nan, you can never really tell what's inside the nan. So I ended up using type confusion to solve this problem. ActionScript has this good property where if a float is in memory and basically you don't access it in ActionScript and you don't do math on it in C, it won't be corrected until it's actually accessed. So long as something's a float, but you cast it to an int every time you do arithmetic on it, it won't get corrupted. So I ended up doing this and basically never performing math on a float. So I started off doing this converter. It's a type confusion converter. And on one side, you have the color matrix filter, which has a float. And on the other side, you have the glow filter, which is an int. And then you can go back and forth and cast an int to a float, except this doesn't actually work. This is one of the more interesting things that led to unreliability that I think is something that you might not expect when you started. Basically, the problem with this is that this array of color filters, when you access it, even if you access like element 1, it actually copies the whole thing to an array in ActionScript. And when it does this, it converts everything to a number because colors are numbers, including things like objects where it might say call value of on them or that sort of thing. And even worse, because the blur filter that I'm confusing it with is tiny, it extends onto the heap. So there's a very small but real probability that it will get a random object off the heap, try and convert it to a number, and then just dereference an invalid pointer and cause a crash. So this works fine for the float to int, but for int to float, you risk this crash condition. So I ended up doing another float converter for the other direction, and this is fine, mostly. There's one more problem here. This actually took a while to diagnose, but strangely enough, in Flash, floats are never represented as floats when they are stored. They're represented as doubles. And then we discovered that this assembly, when you cast a float to a double and back, in one situation, it will actually change the value. And that's because the floating point specification supports S-nans and Q-nans. Q-nans are quiet nans. If you get a Q-nan, nothing happens. It's just stored as a Q-nan. S-nans are different. They're called signaling nans. And according to IEEE 374, depending on the alignment of the planets, at some point they may throw a floating point exception. So this assembly basically corrects an S-nan to a Q-nan, so you're not spuriously throwing exceptions, but it also has the problem that then you lose the value. So I can detect this case, which means my exploit will fail 1 out of 512 times, but it is detectable, so if this ever happens, my exploit just exits. So at this point, I'm going to start ignoring floats, because I honestly never want to think about them again. So this explanation I'll be talking about setting floats to pointers, pointers to floats. Just imagine I'm running it through that converter every single time I do math on it. So the next thing I wanted to do was move the instruction pointer. And to do this, I had to basically create a full fake bitmap object. When I got the vtable, it was enough that I just fetched the vtable. But when you're setting the instruction pointer, you have one more thing you have to worry about, which is it's not enough to just overwrite a vtable. You have to actually be able to call something on that vtable. And the way the bitmap works is there's a bitmap with a pointer to bitmap bits with a pointer to a vtable, and all the calls are actually on that bitmap bits. So I had to create a fake bitmap with a pointer to a fake bitmap bits with a pointer to a fake vtable to move the instruction pointer. So I did this using type confusion. So to start off, I used this float matrix constructor, and that allows you to create a float matrix with whatever you want in it, with whatever size. And then I used these coordinates in the displacement map filter to fetch it. And I did this again, and again, and again, to create 3 objects with pointers to each other that emulate the bitmap object. And then, after that, there was one more thing I needed to do with a pointer to a bitmap data object, and that was to make ActionScript actually think it's a bitmap data object. So I did that by setting the colors on this bevel filter, and then confusing it with something with the bitmap data pointer in the same spot. And then you have something that it thinks is a bitmap pointing to this fake bitmap. So then, all I have to do at this point is to call a method on it, in this case setPixel32, and then I'm executing the fake vtable. So one thing I glossed over a little bit is what is in this fake vtable. And I created it using a method called COP, call-oriented programming, that Chris will talk a bit more about later. But basically, it's a method for creating a series of gadgets that exit very cleanly. So you can see the ritual call enters at the left, and then it calls into the first gadget at the top, and that sets RDI, which sets the parameter to system as gedit, then that exits, and then it does the next call, which actually calls system, and then adjusts the stack and exits cleanly. So that's nice. It means not only does it call system, but it doesn't crash afterwards. So why is this bug reliable? Well, I think the best, or the most important part is just the high quality of bug. All those object members line up, and you have a lot of different options, so that's great. The other thing is that the object members are mutable. They're like basically as mutable you can get. You can read and write every single property, and that's important in making this reliable. The other thing that's good is that the type-confused objects are fairly lightly used. Sometimes you'll have problems with, say, threads running and causing something to crash, but in this case, I was able to just set the movie clip object to 0 by 0, which means basically the threads that typically use these objects won't run because there's no pixels in the object. So that deals with reliability that way. So what makes it unreliable? Well, float conversion, 1 out of 512 times, it just won't work. The other problem I had was garbage collection. It's not sure if it's obvious from the diagrams, but when I type confuse the 2 objects, it's not actually the same object. It's making a copy every time, which is fine for the exploit. But then when you get to garbage collection, you have all these like half objects on the heap, and that's fairly bad. So what my exploit actually does is every time it makes a filter, it basically pops it into an array so that you always have a reference to it, and it will never attempt to garbage collect it. And that's fine as long as Flash is running, but as soon as Flash goes away, for example, you refresh the tab or close the tab, it'll cause a crash. And it's actually not a visible crash, so a user wouldn't notice, but it could create a crash dump, which might be noticeable. And I think you could probably prevent this problem by, instead of calling system, calling an executable that actually fixes the memory space. But my exploit doesn't actually do that. So one last question is, now I've got 1 out of 512, or I guess 511 out of 512 times working. Could I make this 100% reliable? I think there's a few options. The most obvious one is to just stop using float buffers. That's the cause of the problem. If I could find a different buffer, that could fix up the problem. Another option would be to have a set of different gadgets, because it only fails when the pointer is an SNAN. But if you had enough gadgets, you could say, well, mathematically, they all can't possibly be SNANs at once. And then that might be a way around the problem. Another way would be if I could find a way to write an integer into that float array, maybe using a pointer to a different object. So now that I've told you everything that is wrong with my exploit, I'm going to attempt the demo. As I said, there is a 511 in 512 chance that this will work. Oh, and it worked. Yay. Yeah. Just doing it again, probably should have explained what's going to happen first. Is this, as I said, will just spawn gedit when you open up the browser. Oh yeah, that time worked as well. So I'm going to pass it over to Chris now to show his exploit.
Awesome. All right, we've got the mic going? Excellent, thanks. All right, let's look at another 100% reliable exploit. So before we get into the exploit, we're just going to briefly cover what the bug is. It's a problem in an area of Flash called shaders. Shaders are little virtual programs you can run, if you like, that output images, basically. And Flash has this shading API. And what you do is you pass in your shader definition to Flash, and it will compile that, not to real code, but to a little virtual shader execution language. And then you can run that to generate an image. And when you do this, as you can imagine, you might want to pass inputs into your shader program. Like, for example, if you're going to use a shader to render a circle, you might want to pass in the radius of the circle as a parameter. So we have not just a shader object at the API level, but we have a shader parameter object in the API. And after you compile a program, if it declares itself as having inputs, you get these. You also get some shader parameter objects back. And then when you go to run the shader to render the circle, for example, you set your parameter to be radius 10, and then internally at runtime, that input value gets sort of written back into the program just in time, just before it's run, so that the program can run with the values you choose. So far, so good. That's the expected case. Of course, you might want to run a slightly more complicated program to, this one is like twice as long, and we're setting a parameter at position 18 in this one. Again, all working as expected. Where it gets interesting and where the actual bug manifested is what you could do, which is a bit sneaky, but you could take the shader parameter from the longer program and associate it with the shorter program and then run that combination, and oops, you've got a length 12 program and you've written a parameter value at position 18 relative to that program that's out of bounds, and that's heap corruption, and that's the bug. This is CVE 2015-3105. It's long since patched, it's been patched for at least a month. And that's the bug. I thought it was quite an interesting bug. So how would you go about exploiting that bug? Well, the traditional way to exploit that bug, and this is, if you see a Flash exploit, either written by a defensive researcher or one turns up in the wild being abused, almost all of them, interestingly enough, use exactly the same technique to exploit a heap corruption in Flash. So what you do is, if you've got a heap corruption, something going off the end of a heap chunk, what you do is you do a bit of what's called heap grooming. So you arrange for another type of Flash object called a vector of uint to be just after the object where the corruption occurs off the end of, and you clobber the first field of this vector of uint, which is a length, and you make it bigger, and then suddenly you're kind of all done already when you've done that, because when you've got this vector of uint and you've corrupted its length to be bigger, you've got this wonderful exploitation primitive where you can arbitrarily read and write off the end, and you've basically got full control of the process's memory space at that point in time, and from there exploitation is pretty easy. So exploiting something this way, the traditional way, is it reliable? It is not. So what we've done here is, and Natalie covered this in her part, but what we've gone and done here is our exploit has done what we call crossing a heap chunk. And that is not a 100% guarantee to succeed operation. As in, we cannot be sure that when we cross the heap chunk, that right next to our object that goes a bit wrong is a vector of uint. We can't be sure that that is the case. Because when we use this technique called heap grooming or heap spraying, that's a probabilistic technique. You can get the probability of succeeding in getting this layout quite high, but 100%, no. So this is where we have to challenge ourselves. So we've got this very interesting bug. And we've said that a traditional exploitation technique is not 100% reliable, and the goal of this research is to make something that is 100% reliable with the same bug. Can we do better? The answer turns out to be yes. So we actually have two possibilities when we abuse this bug. We can either do an out-of-bounds write, which is where we've crossed a heap chunk, game over, not reliable. Or what we can do is we can do an inbounds or within the heap chunk bad write. So what we can do is instead of taking our shader parameter that's from a different program that causes things to go wrong, instead of taking a shader parameter that's way out of bounds relative to our current program, we can grab one that's in bounds relative to our current program, but pointing to a different opcode, an opcode that is not supposed to be used for input parameter resolution. So when we realize we can do that, something interesting occurs. Like I was looking at this, and initially I thought there were no good possibilities to go forward using this corruption primitive, but it turns out there is exactly one way forward when you exhaustively enumerate the possibilities. And there's this opcode called a ternary opcode. If you're familiar with the C language, you'll know what this is, but it's an opcode that's kind of doing quite a bit of work with just one opcode, and that means that it uses all of its parameters. arg4 is the one of interest here. So another way of putting all of that is within this virtual shader execution language, there are only two things that use arg4, and that's resolving input parameters and the ternary opcode. So the fact we've only got one path forward is both really good and really potentially really bad. It's really good because as an exploit writer, if there are a limited number of paths forward to investigate, that's good. You don't have to worry about missing something. You have to just plow forward using the one path that might get you somewhere, and that feels kind of good because you know that you're either going to succeed or prove definitively that it cannot be done. And it's really bad because you might end up with a dead end. So let's look at the story so far and see if we're going to proceed forward with 100% determinism and reliability or hit a dead end. So we've done a within heap chunk out of bounds write, and that's deterministic, 100% reliable. And we found that there's exactly one side effect that we can carry forward to see if we can get further with this. So we've corrupted the fourth argument to a ternary opcode. The ternary operator, written out in a C-like syntax, looks like this. And it turns out that we're messing up source register 2. And we can set that to whatever we want. So what actually happens when you compile one of these shader programs is it looks at how many variables you're using. They're called registers. Say you're using 8, and at runtime it will allocate space then for 8 registers. We can corrupt this source register and, for example, reference register 100, and that's out of bounds. So in effect, we've turned an out-of-bounds write into an out-of-bounds read. Kind of doesn't sound great. As an attacker, an out-of-bounds read is usually a less powerful primitive than an out-of-bounds write. So perhaps it sounds like we've downgraded our capability here, which will be disappointing. But let's keep with it. Let's see if we can proceed forward, keep our 100% reliability, and get somewhere. So where things turn in our favor again is that at runtime, there's this kind of Franken object that's unusual to see in programs, but this is what we get. So we get these sort of registers that we talked about, say 5 runtime registers, concatenated in the same heap chunk with a C++ object, bolted right next to each other in the same allocation. That's a fairly unusual construct, but this is going to help us. So what happens if we read using our corruption primitive register 1000? Well, that's going to go way out of bounds relative to this heap object here, and we'll cross a heap chunk and game over. As we covered earlier, we can't do that. So again, we've just got one other possibility, which is what if we read inbounds? So at this point, things start to really look up. So if we've got 5 registers at runtime, and using our corruption, we read registers 6, 20, and 30. These are all inbounds reads denoted by the green here, and we can read some really interesting things. One of the things we can read is a vtable, and that's one of the most important prerequisites for defeating ASLR, which is a modern protection that can get in your way as an exploit writer. The other thing that's really awesome is, for some reason, this Franken object at runtime here has a pointer to itself, and that's really useful because suddenly you start to know a lot about the heap layout. You know the address of an object in memory, and is another component in defeating ASLR. So things are looking better. Let's see if we're getting somewhere. What have we done so far? So this is where we're just going to check that we've got our 100% reliability still. So we did a within chunks out of bounds write, deterministic, reliability is cool. That's enabled us to do an out of bounds read. We've decided we're going to do a within chunk out of bounds read. That's deterministic. Our reliability is still with us. We've leaked the value of some really useful things. Awesome. But it's still just a read. I said, as I was reading the slide, I said, but you can't take over a process with a read. Until it occurred to me that James Forshaw did this. He spoke earlier. He's got a blog post that's linked in these slides where he actually did take over a process with a read. So I had to correct myself there. But this type of read we have here is not the type of read that's going to help us take over the process. What other primitives do we have? Well, we know we can cross heap chunks and do cross heap chunks out of bounds reads and writes, but we've kind of written those off as not being reliable because we really are doing everything. We're really going to insist on 100% reliability here. So those are all the primitives we have. Are we at a dead end, or can we put all these pieces together? So there are a couple of realizations that when we chain them together, we realize that there is a path forward here. So let's see. When I say we know our own address, go back to this slide here. At runtime, we've run a shader program that's done these dodgy reads. We've determined the address of our own shader object in memory. And that's kind of cool, because if we know the address of our own shader object in memory, we know the address of the next thing in memory. And if we know a little bit about the heap implementation, maybe knowing what address corresponds to the next heap chunk, maybe we can work out if that will actually fault or not if we do that read. So that suddenly is very interesting. We'll cover the exact mechanics of this in a minute, but we do get to the situation where by knowing our own heap address, we know whether it is safe to read out of bounds or not. And that is to say, we can answer the question, if we read out of bounds, what will happen? And the two options are crash and do not crash. So the second realization is, if we can do a safe out of bounds read, maybe we can use that to prove that our out of bounds write is actually going to write what we think it's going to write. So if we go back to, where should we go back to? Go back to this slide here. What we want to do is we want to line up the heap like this, so we're clobbering this length. But we want to kind of prove that our shader program is next to this vector. So we can use our out of bounds read, our safe out of bounds read, to prove that in fact we did heap groom to this state here, and then we can proceed with 100% reliability, clobbering that length, and knowing that when we do the clobber, that length is there. Right, let's put it all together. So what we're going to do is we're going to heap spray to this attempted state. And when I say attempted state, I mean we do our heap spray, and we think this is where we ended up, but we're not sure. But we're going to use the primitives that we have to prove that this is where we ended up. So we're going to line up a bunch of 8 kilobyte chunks in a row. We'll probably do that by just spraying a bunch of 8 kilobyte chunks in the heap to fill in any holes that may be in the heap. And then we'll spray a bunch more, and in theory, the heap implementation will just line them up in a row, because that's what heap implementations tend to do. Once we've done that, we are going to run our shader that reads its own address, and that will read, exit, and then free itself. But from that process, we'll get back a heap address, and there's a sample heap address on the slide. And that's kind of cool, now that we know that heap address, because when we run that primitive again, I missed a step. So after this thing exits, we then allocate our heap groom object. That's the 3D object here. This is the object that, if all is well, we want to put there, and we want to prove it's there. And if it does end up there, we can use the vtable on that to gain code execution. So what we do is we run that whole cycle through again. We run a shader. It kind of proves to itself its own heap address. And if our heap groom is all going well, like if things are at runtime as we've drawn them on this slide, then we know what address to expect. It's 8,000 bytes or 8 kilobytes less than the previous address. So 7,000 hex goes to 5,000 hex. So what we can do is we can check our address. If it turns out it's not what we expect, then our heap groom has not succeeded successfully, and we'll do what Natalie termed an abort. So that's a safe exit of the exploit without doing a noisy crash that might signal something is going on. But if it is where we expect, we've proved it's safe to do an out-of-bounds read, and then with that out-of-bounds read, we can prove or disprove our theory that the 3D object is next. So this sort of proceeds a bit more using exactly the same primitive over and over again to like prove that what we thought happened did happen. So we're slowly building up backwards this list of objects that are like getting all our ducks in a row, I guess, but these are not ducks, these are flash objects. And eventually, there are actually 5 objects we care about. Once we've proved that they're all in a row, we're actually in a really good place now. We've got this shader program, which is the second object along, and that's where we have this bug where we can write out of bounds crossing a heap chunk, which normally would be reliability done, you're done. But what we've done is we've proved that this vector of uint is exactly 2 objects next to us in the heap. So when we do this out of bounds right, we know with 100% certainty, deterministically, that we're going to clobber what we think we're going to clobber. So we clobber the vector of uint length, and then we're done, because that gives us access, read-write access to the process's memory, and we're going to take over a vtable on this 3D object and calculate. So let's do a demo. So I'm going to tempt the demo gods. The demo gods were not kind to me earlier this year at CanSec, so I'm hoping that they're going to be kind to me today. So we'll run my exploit. There's a calculator. But before we get too excited, let's just drag this over here. When you've got an exploit which you can plausibly claim is 100% reliable, what does it look like an exploit like that? So and this is not in a VM, this is live. And it could, for the first time I've seen, die any minute, and then I'll look really silly for claiming it's 100% reliable, but I've not seen it die yet. That's a lot of calculators. Right, that works. I'm going to really tempt the demo gods. Because that was nice, a lot of calculators, but that was a very fresh process state. I just launched the browser, which just launched the Flash process, very clean heap state, quite easy to get a reliable exploit with a clean heap. So I sort of found this Flash file here, just like a 3D demo, and for whatever reason, it seems to really churn the heap in the background. I don't know if you can see, this is not just a static image, there's a little bit of motion there. You probably can't see it, but the water is like shimmering a bit. This is like 60 frames per second 3D rendering going on, and the heap is being tortured in the background. So let's see if we can still calculate. So we didn't calculate a few times in a row, but we didn't crash. Notice that I don't know if you can read it, but it says stopping, incorrect prog heap address. So at some stage during that lineup of objects that we were doing one by one of them didn't turn up in the right place. We were able to prove that in a safe way, so we just stopped. If this was a real exploit, if that happened, it would just rerun itself. And eventually, it will calculate. See, it got like a 20% calc rate maybe. I mean, this exploit runs in milliseconds, so if it's a real attack, run it 10 times, it's going to succeed, even when your heap is like being tortured. So the demo gods, whew. They didn't give me CanSec, but they gave me ShakaCon. Thank you, demo gods. I hope that's not too many calculators to bog down the rest of the presentation. So I did the demo sort of halfway through. I don't know why. I felt like demoing at that point. Just a few more notes on some of the technologies we use to get an exploit that reliable. You've probably heard a lot about ROP and ROP chains. I don't like ROP or ROP chains. I use COP. ROP, of course, is return-oriented programming. It's well documented in the literature and at various security cons. I've not seen much about COP. It is a term that has been used. I'm not claiming this term. It's a term that's been used before. The best reference I found is in an academic paper, which describes something similar pretty similar to what I've done. But COP, basically, instead of having assembly gadget return, you have assembly gadget call. Why is that so much better? Well, there are some significant advantages to COP. The main one, I think, is there's no what's termed a stack pivot. So if you're doing ROP, you do this thing called a stack pivot. Stack pivot is a tricky gadget to find, especially on 64-bit. And should mention both Natalie and myself did demos against 64-bit processes, mainly because it's harder. If you want to claim 100% reliability, you should go for the hard case. Detectability is really interesting for a ROP chain. So once you've pivoted your stack, if you make a mistake after you've pivoted your stack and before you've got successful code execution, you've just given out a really noisy signal. So there's a lot of crash dump analysis going on right now in the world at scale as crash dumps sort of fly here, there, and everywhere. And I don't know this for sure, but I'm pretty certain that that there are alarm bells going off if you crashed whilst your stack was pivoted, because that's looking at a crash dump, it's fairly obvious that there's a stack pivot going on if you look at certain signals, and that's a big signal that maybe an exploit is underway and it failed. COP does not pivot the stack, does not have that problem. COP gadgets are a pretty common instruction sequence. For my exploit, I used 3 gadgets. I found them all by hand. I think that's proof that they're easy to find. I didn't have to use a program to find them for me. Whilst a series of COP gadgets run, the stack's always valid because the call instruction automatically does the stack management for you. And continuation of execution is pretty easy with this as well. So by continuation of execution, we mean that after you've popped the calc, the process is still stable. When I was popping all those calcs, that was the same process that had been not damaged during popping each calc. So continuation of execution is good with COP because you didn't pivot your stack, so you don't have to unpivot your stack. Unpivoting the stack can be difficult. So Natalie went into this a bit, but to do a COP, you set up your fake vtable a bit like this. So the fake vtable is interesting. So at the beginning, we've put a string, which is what we're going to execute. Gnome calculator is the name of calculator on my Linux distribution. And when you enter the vcall, the first vcall into the exploitation sequence where the vtable is corrupted, at least on Linux, the compiler that seems to compile Flash and Chrome likes using the RAX register as the vtable register. So we come in with RAX controlled and pointing to this buffer. Starts with gnome calculator, and then the vcall is at position hex 70, so that's our first gadget. So what we do there is we just copy RAX to RDI, and all that's doing is pointing the RDI register at the gnome calculator string, so that when we call system, the calculator will pop up. We then jump to gadget 2 at hex 50. Gadget 2 jumps to gadget 3 at hex 20, that jumps to system. And then the unwind sequence is pretty sweet. So the second gadget, which I found very common, just adds a little bit to the stack and then returns. So depending on how many COP gadgets you chain together, you just add the right amount to the stack in your last gadget and have it end in a return. And the exploitation sequence, I never actually counted them, but it's like, how many? It's like 7. Well, the first one is the vtable call, which is part of the real code, but our fake code is 6 instructions, and then we're done. So I guess that may factor into the reliability, the fact that we did something so simply. It's worth mentioning mopping up, so continuation of execution. Again, because we had this 100% reliability / determinism thing going on, that kind of meant we were operating with quite a bit of care. As in, when we did actually perform the actual corruptions that let us take over the process, they were very small and precise corruptions, done in a very careful way. So undoing them, we didn't have any sort of shotgun approaches going on at all or anything like that. So undoing what we trash is easy. We trash 2 small things. Undoing them is as simple as repairing the vtable that we trashed. So the same out-of-bounds write that we used to set the vtable to our fake vtable, we just set it back to what it should be. That was easy. That's the first thing we trashed. The second and only other thing we trashed is the vector length. Well, it turns out that we trashed that length by running a shader program that trashed the length. We can just rerun the same shader program, but with a different input parameter to put it back to the original value. So again, simplicity is what is helping us get reliability here. So let's just summarize what we did. It sounds complicated because there's a lot of steps. But remember, it doesn't matter if you've got 10 steps or 100 steps. If you know that each step is deterministic, you can have as many steps as you like, and things will always work out for you. So we did a within chunk out-of-bounds write to corrupt an opcode in our shader program. We'll use that to do a within chunk out-of-bounds read to grab some useful stuff like a vtable and the self heap address. Using the self heap address's knowledge, we did a between chunk out-of-bounds read, but we know it's safe because we had knowledge of the heap addresses involved. We used those safe but out-of-bounds reads to prove the heap layout of 5 very important objects was, as we expected, all in a row. And then we used our between chunk write to clobber the field, a known field of an object, And that works because before we pulled the trigger on that, we proved that the heap was lined up exactly as we needed it to be. And then a bit of COP, we discuss whether that's reliable, then we repair the damage, and yeah, success. But we should always need to be asking ourselves this question. When we're trying to do 100% reliable exploitation, you always need to be asking yourself, is it reliable? Is there some source of unreliability I didn't think of? Is this one reliable? Well, it looked reliable, didn't it? But if we're being honest, I can't claim this is 100% reliable. Let's look at why not. So there are some common sources of unreliability you should always be asking yourself about when you're doing an exploit. The first one you should ask is, what about threads? Threads are a giant pain in the ass. They're asynchronous, they're hard to understand, they're hard to reason about. So what about the exploit that I demoed just now versus threads? So I'm grading myself here yellow, sort of okay. So the most likely thing a thread is going to mess us up on is, whilst our exploit is running in one thread, another thread is going to be doing something, maybe rendering some 3D stuff on the screen, right? And it itself will be allocating and freeing objects from the same heap, so it might mess up our heap groom. Well, that's okay. We'll detect that cleanly using our safe primitives, and we'll exit. So that's okay. But the reason I'm giving myself a yellow, sort of okay grade is this next statement here. I do not believe that a thread will touch the corrupted 3D object during the window of corruption. So that's to say, as I think the exploit is 100% reliable in this regard, but I haven't proved it. To prove it, I would need to study that area in quite some depth and spend quite some time on it to prove that's the case, and I haven't done that. So although I think it's cool, I can't claim it's 100% reliable because I haven't done the work. So that's yellow, sort of okay. What about page reload? So page reload is like hitting refresh in the browser. And the page reload is a tricky case because page reload sort of shuts down everything and restarts it. So in the case, when you're shutting everything down, you're sort of touching every object in the heap and deleting it and destroying it. So if there's a slightest mistake you've made, you're going to know about it. Or if a page reload occurs right in the middle of your exploit running, whilst things are in a dubious, in the middle of exploitation state, you might explode. We think we're okay here because the way page reload works in Flash is that it's synchronous with respect to running script. So as long as you don't exit your script whilst your exploitation is half done, as long as you make sure you're fully done before you exit, you'll be fine because the page reload event will only be handled after your script is finished running. So we're giving ourselves a green for that one. Out of memory pressure, you should always ask yourself, when my exploit's running, the process I'm exploiting could be in any sort of state. It's hard to tell, right? So what if this process is just low on memory? What's going to happen there? So there is a case that will cause us trouble here. So in the Flash heap, when memory's getting low, this low on memory panic signal gets sent around all over the place. And one response to that is to start decommitting pages in the heap. And that's a problem because a decommitted page, you touch it, you blow up. And that's kind of annoying because you might prove that an address is a valid heap address. Then it gets decommitted and you touch it and you blow up. But we're still giving ourselves a green grade here because you can actually, there are rich APIs in Flash to query system state, including how much memory is free. So you can tell if you're in a tight spot or not and act accordingly. Finally, what about unusual virtual address space layout? And this is the problem that caused Natalie some trouble with her floats. But I'm giving myself an iffy grade here because I actually managed to understand the problem sufficiently here to understand and describe a problem here. So due to constraints of the shader language, when we're doing those comparisons of where am I on the heap, is it where I expect, it turns out I'm only comparing the lower 32 bits of a pointer. And this is a 64-bit exploit. So it is possible that if the heap gets really big and spans 4 gigabytes, you can have 2 pointers that look the same on the lower 32 bits. And one of them could be safe to read off the end off, and the other one might not. So I'm giving myself an iffy grade here, red, because I can describe a situation that would cause a crash in that exploit. It's not going to happen in normal Flash processes. And also, I think I could repair it, which is I would do if I were taking this any further. But I have to give myself a red grade there because I understand a condition that will deterministically fault, even if it's like 0 likelihood. So let's conclude. So during this research, what dominates whether you can create a reliable exploit out of something or not is the bug that you start with. So that is to say, if you don't start with a good bug, a good bug class, you're probably not going to get very far. Conversely, even if you do find a really good starting bug and proceed forward with it, 100% reliable exploits are hard. I think we thought when we got into this, when we both started with awesome bugs, that we were going to have like a 3-step exploit and we're done. And we've both ended up with like 20-step exploits where we've struggled to keep our hands on determinism at each step. So it was hard, which was a bit of a surprise. And we also found some factors that are difficult to control for. So we were quite surprised that virtual address space layout caused so many headaches for us, but it did. That was a surprise. And when we started thinking about threading, I think we gave ourselves headaches just overthinking threading, because threading is just difficult to think about and reason about. And finally, one question people have asked about this research is, can you use this research profitably for defense? And the answer is yes. There are a couple of reasons for that. One is that we think you can't defend fully. You can't defend with maximum potency unless you really understand the extreme limits of what's possible in attack. So by trying to make some of the best pieces of attack research possible, 100% reliable exploits, that's given us some insights that we weren't expecting to gain. But now that we've gained them, we're going to use those insights to start thinking about, well, where could we have broken that 100% reliability with little defensive tweaks? And we're definitely going to carry that forward over the next months and hopefully be blogging about some ideas and perhaps even landed solutions soon. So with that, thanks very much for listening through a pretty intense technical couple of exploits. And if we have time, we'd be happy to take some questions. Over here.
So what really prompted this was the ability to have demos that were reliable at conferences?
So what really prompted this was the ability to spew calculators in a perhaps. All right, I think we've flattened everyone with just the sheer volume of technical pace. One more at the front here.
What about releasing your proof of concepts on Metasploit for other people to release?
Yeah, great question. What about releasing what we've just seen? So for those of you that saw the keynote earlier today, we really believe in doing everything we do it in the open. And that means we release everything we do. So over the next days, we'll be releasing the slides. We'll be releasing blog posts that have slightly more accessible, perhaps, descriptions of what we've just seen. Along with those blog posts, there'll be links to the actual raw exploit materials. So yeah, follow our blog here, and over the next days/weeks, everything will be released. We just have to, we just have to tidy up the blog posts and get it done, really. But yeah, coming very soon. All right, well, thank you very much.